Here are two general lines in space. They're not parallel, and they don't meet. In fact, they have a special name. They're called skew lines. Clearly, any problem involving two lines like these in general directions is going to be something that can be tackled using vectors. And the very fact that it's so general means it's going to be tricky to visualize. What we're actually going to do is to calculate the shortest distance between these two particular skew lines. That's what we'll be working towards in the program, their closest distance of approach. And when you do this using vector methods, you'll find that involves dot and cross products of vectors. But before getting on to that, let's look again at the lines the way you first saw them. They look as if they're parallel, but we know they're not. It all depends on your point of view. Now, let's take that idea a bit further. What, from your point of view, does this look like? It looks like a regular hexagon. But it's not. And the reason it looked like a regular hexagon was because of the projection you were looking at. Look at the lines again. They look as if they're parallel. That's because you're looking at a particular projection. This looked like a regular hexagon because, again, you were looking at a particular projection. Now then, what do we mean by projection? And can we express projections in terms of vectors? John?
Well, before we do that, let's see what can be done with vectors. There are four basic operations in vector algebra. We can add two vectors by the triangle or parallelogram rule. We can multiply a vector by a scalar, and that's called scaling. And we can multiply a vector by a vector in two ways, the dot product and the cross product. Now, you've spent some time in the text looking at addition and scaling, so let's take a close look at the two products of vectors. First, then, the dot product. We have a vector A and a vector B and an angle theta between them. Then the dot product of A and B is defined like this. It's the magnitude of A times the magnitude of B times the cosine of theta. Well, this quantity here is a scalar quantity. It's a real number. What do you think the dot product has to do with projections? Well, let's take a close look at what we mean by a projection. Here is a vector, and here is a direction. We obtain the projection of this vector on this direction the following way. We drop a perpendicular from the head of the arrow to the line, and then this distance from the foot of the perpendicular to the tail of the arrow is the projection of this vector in this direction. It's the same thing for any direction. Here's another direction. Drop a perpendicular from the head of the arrow to the line, and then this distance is the projection of this vector in this direction. We can easily calculate the length of a projection of our vector. Starting with the vector A, draw in the line we are projecting onto at an angle theta to the vector. Then drop the perpendicular, and this is the distance we want, which is just the magnitude of A times the cosine of theta. But if this line was in the direction of a unit vector E, then the dot product, A dot E, that is the magnitude of A times the magnitude of E times cos theta, will give us the same answer, because the magnitude of E is 1. It's a unit vector. So to summarize, if we define a direction by a unit vector E, then the projection of a vector A on that direction is just A dot E, the dot product of two vectors.
Now, that's fine for projection on a line. But what you actually see on your television is a projection on a plane. At the moment, you're seeing a projection of me on your TV screen, which prompts two questions. Precisely what do we mean by projection on a plane? And how can I extend what John's just done to express it in terms of vectors? Let's start with a vector and a plane. Common sense tells us the answer. To see the projection on a plane, we simply look at right angles to the plane, like this. You now see a vector which looks like a vector lying in the plane. It's the projection on a plane. If I put in a unit vector normal to the plane, and the camera looks along that unit vector, then you see a vector that's the projection on the plane. You see a vector that looks like this vector. And it's one you can calculate. You can calculate it from the triangle addition rule. I put in another vector at right angles, then it's this vector plus this vector will give us the vector we started with. Let's call our original vector A. And let's call the normal to the plane E. Then we can work out the projection of A on E. It's A dot E. So this vector is of magnitude A dot E in direction E. That is A dot E times E. Now then, using the triangle addition rule, the projection on the plane is simply this. A minus A dot E times E. That's an awkward looking expression which prompts the question, is it worth having? Let's see the kind of question it's useful for by looking at the hexagon again. From here it looks like a regular plane hexagon, which means this angle looks as if it's 120 degrees. The question you're in fact asked in the text is, what is this angle really? And you're given two pieces of information from which to work it out. You're given the length of a side. Let's measure it. A length of 156 millimeters. And you're also given the height of the hexagon above the plane it's on. That is this height. We can measure that too, and we find it's 90 millimeters. Now, I'll give you a start on this question. First, define some vectors. We'll call a vector along this side A, and call this a vector B. You'll also need to define a unit vector normal to the plane. Call that E. That means that in knowing the lengths of the sides, you know mod A and mod B, and you also know the magnitude of A dot E and B dot E. That's that depth. Now, the next thing you do is write down the projection P and the projection Q. You can write those down, P in terms of A and A dot E, and Q in terms of B and B dot E. Then you can form P dot Q in terms of A dot B, and you know the angle between P and Q. You know that this angle is 120 degrees. So from there you can do the problem.
Well, you've seen one way we can use the dot product of two vectors. So let's look at the second way of multiplying vectors, the cross product. Given a vector A and a vector B and an angle theta between them, then the cross product of A and B is defined like this. Notice that it's different from the dot product. This time we have a sine theta in here. The vector product of two vectors is a vector quantity. The direction of the vector is given by the unit vector c. C is perpendicular to A and perpendicular to B. Now that gives us two directions for C. C could either point out of the board or into the board. And we need a convention or rule to tell us which direction C points. Well, the convention is the right-hand rule, which says the following. We take our right hand and we use the thumb to represent the direction of the first vector, A, the first finger to represent the direction of the vector B, and then the middle finger represents the direction of the unit vector C. And if we line our thumb and first finger up with the vectors A and B, we get the direction of C, like this. The thumb represents A, the first finger represents B, so the direction of C is out of the board. Well, there are several applications of the cross product in geometry, and here's one of them. Here are 3 points in space. Now, just as 2 points are sufficient to define a line in 2 dimensions, then 3 points will define a plane in 3 dimensions. And here's the plane through these 3 points. Now, how can we describe that plane in terms of vectors? Well, this is the way we do it. Here is a vector perpendicular to the plane. Now, clearly, there are 2 such vectors, one pointing out of the plane and one pointing into the plane. But it's not the direction of the vector that matters, it's the orientation, the fact that it's at right angles to the plane. Well, how can we find that vector? Well, let's go back to our 3 original points. If we're given 3 points, we can define 2 vectors. This is the vector of that point relative to that point. And here is a vector of this point relative to this one. Now, the cross product of these 2 vectors will be perpendicular to the 2 given vectors. These 2 vectors lie in the plane, and so the cross product of these 2 vectors will be perpendicular to the plane. Now, what we're interested in is the direction. And the direction is given by a unit vector. Well, if this vector here is this vector cross this vector, a unit vector is A cross B divided by the magnitude of A cross B. And so the unit vector n, which is perpendicular to the plane, is A cross B divided by the magnitude of A cross B.
So we've looked at dot and cross products of vectors. Now let's use them. Let's use them to work out the shortest distance between these skew lines. Well, what is it? Where is it? We've got a model that'll give us a clue. It's a model with 2 skew lines joined by a spring, and the spring can move freely. It naturally takes up a position where it's shortest. And there are 2 things you should notice about it. First, there seems to be a unique position. And secondly, with a set square, which I have about my person, look at the angle between the spring and a skew line. It's a right angle. And so is this angle between the spring and the other skew line. So the shortest distance between 2 skew lines will be at right angles to both of them. That looks as if we should use a cross product.
But first, we have to express the skew lines in terms of vectors. So let's choose a vector d1 along this skew line, d2 along this skew line, and a unit vector e along the line of shortest distance. Then, using our definition of the cross product, e is d1 cross d2 divided by the magnitude of d1 cross d2.
Right, so now you know the direction of a unit vector E along that shortest line. But ultimately, we're interested in the length of that line. Start then by defining an origin O, where one of the skew lines meets the floor. Now I want you to imagine a vector R drawn from the origin to where the other skew line meets. And you can see a triangle which has a right angle. That means that the shortest distance is the projection of R onto E. In other words, R dot E.
But we know E, it's just this expression here. And so the shortest distance, R dot E, is just given by this. But before we go on, we need an expression for the vector R.
What do you know about R? It's a vector from the origin, O, to a point on this line with direction D1. So, you put in the position vector of the point where the line D1 passes through the floor. Then, you can use the triangle addition rule to express R in terms of this position vector and the vector D1.
Well, it's this. R is A plus T D1. This is the triangle that Dan was talking about. The vector R is the vector A plus this vector here. And this vector is a scaling of the vector D1. In other words, this vector is something times D1. Well, if we call that something T, T is just a scalar. So that R is A plus T D1. Now, as the scalar T varies, so this vector changes. But notice that this vector always touches the skew line. But we don't know the value of T for which this vector intersects the shortest line. But we'll now show you that you don't need to know that value of T. But remember, we want to work out this. Now, if we substitute for our expression for R, we get this. Now, if we expand this, we get two terms, one involving the dot product of A and one involving the dot product of D1. Now, let's take a close look at that second term, because that's the term involving T. It's this term here. Now, this bit is a unit vector along this line. And D1 is a vector along this line. And these two lines are perpendicular, because this is a right angle. Now, the dot product of two vectors which are perpendicular is 0. And so the dot product of D1 with this vector is 0. And so our term involving T is just 0. And we're left with A dot D1 cross D2 divided by the magnitude of D1 cross D2.
So that's the formula, and it works for the general case. Now let's see it for this particular case, for these two skew lines. You'll need a coordinate system. We've already got an origin, so for convenience, let's take the floor to be the xy plane. We'll call this one the x-axis. This can be the y-axis. And we need a z-axis. The right-hand rule gives us x, y, z. So the z-axis is upwards. Now, let's see how we express the vector A. in terms of those coordinates. We'll have the usual unit vector I in the x direction, unit vector j in the y direction, and unit vector k upwards. To get to the point where D1 meets the floor, we go 8 units in the x direction, then minus 4 units in the y direction, and nothing in the z direction. So the position vector A is 8i minus 4j plus 0 times k. Now, what about our directions D1 and D2? The line D2 first, it passes through the origin. Start on the line, go minus 3 units in the x direction, minus 2 units in the y direction, and plus 4 units in the z direction. And we're back on the line. So, one possible expression for D2 is minus 3i minus 2j plus 4k. Or half that, or twice it. Any scaling you like. It doesn't matter, it's the direction that's now uniquely defined. D1 next. Start on the line. Go minus 5 units in the x direction, plus 2 units in the y direction, and plus 4 units in the z direction. So D1 is minus 5i plus 2j plus 4k.
So now we're in a position to work out our shortest distance. Dan has given us the components of the vectors A, D1 and D2, and all we have to do is plug those components into this expression and we can work out the shortest distance. Well, you were asked to work out this bit before the program. What we get is this: 2i plus j plus 2k divided by 3. And now we have to take the dot product of that vector with the vector A. In other words, we have to work out this expression here. Well, after all this dotting and crossing and jumping about between skew lines, we finish up with the answer 4.
So in this program, we've tried to show you the geometrical significance of the dot and cross products of vectors. The dot product is about projections. It's a scalar quantity. The cross product is a vector quantity, and you get a vector perpendicular to the two constituent vectors. This problem, the skew line problem, is rather abstract, but it's a good exercise in visualizing the products involved, and it's that kind of visualization you'll find crucial later in the course when you come to do vector mechanics.